Okay, thank you and everybody. We're back for our last goal for chapter 16, which is a different kind of reaction that we've learned up to now. In the step growth polymerizations, we're looking at common organic transformations we learned about in the carboxylic acids derivatives, but we're going to do something different here. And in the chain growth system, we're going to involve a new functional group we really have barely introduced called the radical. And what these radicals do is they create carbon-carbon bonds directly, okay? So I'm gonna go ahead and share my screen. There it is, share screen. There we go, and I have to move this up here. And let me put my chat box back here so I can see if you have questions. Uh-oh, is that, no, that's not the chat box. Where's the chat box? There it is. Okay. All righty then, we're back on everything. So let's talk a little bit more about our goal 3 chain growth polymers, okay? So these are a little bit, all the morphology stuff is the same. If there's hydrogen bonding, that controls things. If there's regularity, it makes crystalline domains. Most of these things can be stretched to be ordered, okay? The difference in chain growth polymers is how we make them, okay? So in a chain growth polymer, we typically use a way in which we join the molecules together without losing any other atoms. Notice when we were reacting all of those other molecules for the step growths, we typically lost something like water or a small molecule like ethanol or methanol. So in this case here, we have all the exact same atoms in the starting material, in the monomer, that we have in the polymer. We haven't lost anything. And so a lot of chemical industry loves this because you don't lose any mass when you make the material. It all goes to polymer. You start with 100 pounds of ethylene, you end up with 100 pounds of polyethylene. Okay, so it's very efficient in the way it uses the molecules. Okay, so typically, most of these chain growth polymerizations almost always use a double bond, okay? So we're using that pi bond to create a new sigma bond on both ends of the monomer unit, okay? So there's a bunch of different types we have here. And when we name our step growth polymers, it's exactly like other polymers. We take the monomer name and add poly to it, okay? So in the case of our first compound here, if we take something just as simple as ethylene right here and polymerize it, we get polyethylene right here, okay? And so the cool thing about polyethylene is, you know, it's very simple, it's a very cheap starting material, and it makes a very inexpensive polymer. By adding just a methyl group to it, our ethylene becomes propylene or propene, as the chemists would call it, but engineers call it propylene. And that gives us polypropylene, which is good for fibers and for carpets. It's also good for packaging, okay? By replacing one of the hydrogens with just a chlorine here, we now have vinyl chlorides. So we have our ethylene or chloroethylene, and we get vinyl chloride from that, and so it's PVC. And so that's definitely used in a lot of construction tubing. Right there. If you add a second chlorine on here, that becomes something else. That's dichloroethylene. Dichloroethylene is a copolymer, which means they have two different monomers used in things like saran wrap. Things are really stretchy, really elastic, and hold out oxygen. And just that extra chlorine does that to you. Acrylonitrile is used a lot in the system to make nice fibers. These are very high tensile strength fibers. There's also some cyano compounds like this that are also used in superglue. So we'll see that again. If you take all the hydrogens off and add fluorines, we now have tetrafluoroethylene or Teflon. It took all of the carbon hydrogen bonds away and put a stronger carbon fluorine bond in there. because that carbon-fluorine bond is so strong and nothing will want to break that bond, it actually gives us a non-stick coating because the fluorines, nothing will bond to the fluorines, and so that we get a nice system there. If we replace one of those hydrogens with a phenyl group, we get styrene, and so we can get foam or just regular plastics out of styrene as well. If we take a carboxylic acid and add an ethyl group to it, we can get what we call latex. And that's used a lot in paints. It's also used a lot in the semiconductor industry. These long chain groups are used a lot in the semiconductor industry to help us pattern computer chips. So, and then there's another one right here. If we take another derivative of it and we still have the carboxylic acid group on it, but we add a methyl group to it, we call that methyl methacrylate, okay? And methyl methacrylate is the plexiglass. Remember that polycarbonate is Lexan, polymethyl methacrylate is plexiglass. So it's also very transparent and a very tough material. Okay. So anytime you see a poly and something after it, try to figure out what that the starting material was. Okay. So, oh, this is this is polyethyl stearate. Okay. So what's ethyl stearate? We got to figure out what that is. So you'll be able to see all these different derivatives just by thinking about what the monomer was when you look at these. Okay. So again, we use this in what we call a chain growth mechanism because we do not lose any molecules, okay? And the most common way for us to do that is what we call a radical polymerization, okay? A radical polymerization is not like other reactions where we just have a nucleophile attack an electrophile and it forms a new sigma bond. In the case of a radical formation, we have an unpaired electron. And so we have an unpaired electron attack a double bond. When it does this, it leaves another unpaired electron. So that means we have 3 steps in every one of these radical chain growth mechanisms. The first thing you do is you generate an unpaired electron on the polymer. Then you use that unpaired electron to grow the polymer. And then when you take away that electron or react it with some other single electron to terminate the growth is the last step, okay? So the first step is initiating the chain. The second step is propagating the chain. And the third step is terminating the chain, okay? Most of the times we create these first radicals with the presence of a peroxide. Okay, and peroxide, it just means you have an oxygen-oxygen bond, which is easy to break homolytically. So each oxygen takes the same number of electrons away, so they break that sigma bond, generating 2 single electrons. All right, so let's take a look at that, okay? So up to now, when we draw things happening, right, we draw a double-sided arrow because 2 electrons are coming in from the nucleophile. The 2 electrons are used to create a new sigma bond. Here, we're doing something different. We're breaking a sigma bond and 1 electron goes to each of the 2 components. So we're going to use what we call a fishhook arrow, okay? Which means a single barb means 1 electron and a double barb means 2 electrons, okay? So we just introduced this. This is new to you, but it is, if you think about it, all the other reactions we drew were these 2 electrons moving. So because this is a oxygen-oxygen bond, it is not polar because both oxygens have the same nucleophilicity, so that its most common way for it to decompose with heat is to generate a equal portion, 1 electron on each of the components here. Okay, so this is the first step. This is the creating of the single electron, okay? So once we initiate that single electron, what can happen is that initiator is going to react with anything with a double bond, okay? And when it does that, it goes to what we call the propagation step. Now you have a single electron at the end of the polymer chain that's going to react with another double bond, creating another single electron, creating another double bond, creating a single electron, another double, and continue, 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 until you've basically removed all of the double bonds available for you to react with. After you've removed all the double bonds available to react with, then it can go to the termination step. All right, so let's look at in a chemical drawing way of what's happening here, okay? So I'm gonna start with this initiator here. And again, this would be something where we have an R-O-O-R bond, okay? So this is what we would call a peroxide, or two oxygens together. They're gonna break apart and give us one radical on each of these oxygens here. Once we have this one radical here, we're gonna have one electron reach in and grab one of the electrons out of the double bond. So notice we have a single fishhook arrow here. When it does that, the other electron has to go somewhere and ends up on the other carbon of the double bond, okay? So our initiator started the reaction by reacting with a double bond. Now that we have this electron here, it can react with every other double bond available to it. And when it does, it still only uses one electron from that to make its new sigma bond and one electron from the double bond to make it. So you always have a single electron left over during this reaction. And so it keeps going and going and going and going and going until you run out of double bonds. Once you run out of double bonds, then you end up having to take two radicals reacting together to form a sigma bond, okay? So if you can imagine, after you run out of all of your material with a double bond in it, you end up having the last two chains, the last two radicals available to you, coupled to terminate the reaction. So we have initiation, the creation of a single radical, usually on a peroxide, an oxygen. You have that reacting with a double bond. When it does, it generates another unpaired electron, which reacts with another double bond. Until the final thing, till you run out of double bonds, and then you end up with terminating that by a radical-radical coupling. Those two single electrons get together to form a sigma bond, okay? So the cool thing about these reactions is because of the, there's a preference on where the radical is going to react, because one of the radicals is going to be more stable than the other, okay? Just like in carbocations, the more substituted radical is the more stable radical. It follows the exact same series, which means when we react a compound with a group other than hydrogen here, we have selectivity. It's going to react on this side first. The initiator is going to attack there because it'll generate the more stable, more substituted radical. That more substituted radical is then going to react with the other end of that, of the next molecule over, okay? What that means is that the head of the molecule is going to react with the tail of the molecule. Then this becomes the head of the molecule, and it's going to react with the tail of the next one. And so we call this a head to tail linkage, okay? So it all has to do with the specificity that the more substituted radical is the more stable radical. It'll always form the more stable radical, even during these chain growth polymerizations, okay? So there's a way to, an alternate way is, instead of using a radical to do this, we can use what we call a metal catalyst system. And this but actually produces a carbanion, or a negative charge, just like in a Grignard reaction. We can actually form the same thing with an anion, okay? And the most common way we can do that, and this is how we make a lot of different types of polyethylenes, is what we call Ziegler-Natta catalyst, okay? So it's basically using a magnesium chloride with some aluminum and some titanium. Think about it as forming a carbanion, just like the Grignard reaction. We have that MgBr. It's analogous to the Grignard reaction here, where we're forming the negative charge on carbon, okay? And so the way this works is we actually have a solid support that this thing is on. This is the magnesium chloride particle. That's a 2 right there. And we react with a titanium compound. That titanium compound reacts with another organocompound right here. Notice this is aluminum, and so that means there's an anion right here on the carbon. Once it does that, it generates this as our starting material. And once we've generated that, we can now add to the end, creating an anion, and then it keeps growing and growing and growing and growing. So it's just like the radical reaction, except now we're using anions in the reaction. And so it's an anodic chain growth polymerization. And remember, chain growth means we do not lose any atoms when we build this. And so we're not losing any atoms after we've lost this one hydrogen to start the chain. We just keep growing and growing and growing. Okay, so this is used a lot in making high density polyethylene because it decreases the number of branches. The less branches you have, the more it can pack. The more it can pack, the tougher it is, the more dense it is, the more crystalline domains it has. Okay, so that is our introduction to chain growth polymerization. Okay, so again, polymers are just big organic molecules. We can make them 2 different ways. We can make them like carboxylic acid derivatives, which gives us step growth polymers, or we can use that new reaction mechanism with single electrons called radicals in chain growth polymers. Chain growth polymers have 3 steps. Those 3 steps are initiation to generate a radical, propagation, the monomer has reacted with a radical initiator and will continue to grow until all of the double bonds are gone, and then termination. That terminating, when all the double bonds are gone, those radicals will react with each other because there's nothing else to react with, and it terminates the reaction. All right, questions over polymer chemistry? I'm going to stop sharing and get us back there. Okay, so I want you to know I'm actually a polymer chemist. I did most of my organic chemistry as polymer chemistry, so this is a very near and dear topic to me. But knowing that you can go from small molecule chemistry to making things that make, barrels and barrels of solid materials is kind of interesting. So my sister actually worked for Dow. My brother-in-law works for Dow. So we do a lot of polymer chemistry around the house as well. So, all right. That is the last chapter, chapter 16. We covered chapters 1 through 16 in an amazing number of 16 lectures. So, questions on polymer chemistry first. Again, I'll unmute everybody if you want to talk. If there are no questions, let me pull up the student activity answers from last week. I wanted to talk through that if you guys want to think about that. Or does anybody have any questions about that? Let me ask that first. Chat. Okay, I'm going to stop recording.